In our first lecture on image processing, we talked about how image processing is about transforming an image to a new one that is either clearer, enhanced, or easier to analyze. And here are the topics we covered in our first lecture. We first talked about pixel processing, which is the simplest type of image processing you can apply to an image. Then we talked about linear shift invariant systems. And we saw how linear shift invariant systems were really performing what's called a convolution. And any system that is doing a convolution is a linear shift invariant system, and vice versa. Based on this theory, we developed a few linear image filters. For instance, filters for smoothing an image, for diminishing the noise in an image. Then we argued that there were certain things that we would like to do to an image that cannot be done using convolution, using linear filters. And so then we talked about non-linear image filters, such as median filter and the bilateral filter. And finally, we talked about template matching, which is the problem of taking a little pattern and finding that pattern in an image. And an effective way to do template matching is by using correlation, which is closely related to convolution. In the second lecture on image processing, we're going to start off by talking about the Fourier transform. The Fourier transform allows you to go from what's called spatial domain to frequency domain. And it turns out that a lot of tools, a lot of methods in image processing are easier to analyze in frequency domain. Then we'll talk about convolution, which we discussed in the previous lecture. It turns out that convolution in spatial domain is equivalent to multiplication in frequency domain or Fourier domain. This simple fact, this very important result, can be used to design a variety of linear image filters in frequency domain. Next, we'll talk about the problem of deconvolution. Imagine that while capturing an image, your image is somehow convolved with inadvertently by a function, such as motion blur. In this case, you want to undo the effect of convolution. And so this is called deconvolution, and it turns out that it is much easier to deconvolve a signal in frequency domain rather than spatial domain. And finally, we'll talk about sampling theory. What is being formed on your image sensor, as you know, is a continuous optical image, and then we're sampling it with a regular grid of pixels. There is a sampling frequency beyond which, if you sample this continuous image, you can actually recover the continuous image without any loss of information. But if you undersample this image, that is, if you sample with a frequency that is below that image, it turns out that not only do you lose information, but you might actually introduce new artifacts in the image which are undesirable. That process is called aliasing, and we'll discuss aliasing as well, and how cameras today avoid aliasing.